In this video we're going to be tackling this definite integral, which is the integral from 0 to infinity of x to the power of m e to the negative k x to the power of n dx. So although there are going to be some restrictions that will come about from m, k and n, what I'm doing here, which is what I've said in other videos, is I'm going to start off by not actually showing the restrictions that exist in order for convergence to be achieved with integrals, and where as we go through the integral we will then derive the conditions when they are required. The first one though that we see that must be 100% obvious is that k must be a positive value, and the reason why k must be a positive value is if it was negative then we would have a negative by a negative, which would make it positive, and therefore e to something that is positive going from 0 to infinity would not converge whatsoever. So the first one that we can clearly see that we can force is that k is a real value. In fact, we can actually extend it into complex values, but I'm going to have this as a sole real application, so to speak. And the restriction is that k must be a positive value. So that's our first component. Now, this, you may look at this and you may go, oh, this actually looks very similar to the gamma function. And in fact, actually, with a couple of very, very simple substitutions, which is what we're going to go through, we can position this in terms of the gamma function. This is a nice one to have in your back pocket because, at least for me, when I'm dealing with a lot of other integrals that involve more trickier sort of things involving e to the negative x to the power of something and sines and cos and tans, etc., quite often this integral comes about. So I thought I would go through it very quickly here in this video, and so that way when we call upon it later on we don't have to go through the process of doing it over and over and over again. We can just call back on this video and the result of it. Okay, so the first step that I'm going to do here is I'm just going to absorb the k into the x. So I just want it to be e to the power of negative u to the power of n. And so what we have here, j of k comma n, which is the integral from 0 to infinity x to the m e to the negative k x to the n, is equal to the integral from 0 to infinity x to the m. That remains unchanged. But you'll see here all I've done is I've just pushed this k in with the power of n. So in order to do that here, we just have k to the 1 over n times by x. And, with our indice laws, we see that if we were to push it through, we would have k to the n over n, which would just be the k as we've got. And then we would have x to the power of n, which is what we have here. So the next substitution I'm going to make, a very simple substitution, is I'm just going to let this equal u. So we have e to the negative u to the power of n. So the reason why I'm doing this is I want to draw the k out the front. So we have one less variable within our integral. Okay, so as I said, we're letting u equal k to the power of 1 on n times by x, which means du dx is, remember this is just a constant, it's got nothing to do with x, so we just have k to the power of 1 over n. Rearranging, we simply have dx is equal to k to the negative 1 over n, or 1 over k to the power of 1 over n, times by du. And also we see that just by rearranging this, x is equal to k to the negative 1 over nu. And this is important because we need it here. Now in terms of the bounds, you'll see that they remain unchanged. Because k is a positive value, that means k to the 1 over n is going to be a positive value. No matter if n is positive or negative, this will always be a positive quantity. So if we substitute it in our lower bound, we have u is equal to a positive quantity times by 0, which is just 0. It wouldn't matter if it was negative because it would just be 0. But more importantly for our upper bound, as x goes to infinity, because this is a positive constant times by infinity is just going to be infinity. So the bounds remain unchanged. Okay, and so that's what we have in the next line, j of k comma n, which is equal to this expression that we had before, is equal to, so we'll do this partwise. We see here, for this component here, we've just replaced this with u, so we have e to the negative u to the power of n. Our dx gets replaced with k to the negative 1 over n du, which is what we have here. And then what we've got in this expression here is we've got x to the power of n. Now remember, x is equal to k to the negative 1 over nu, so we have that here, raised to the power of n. So what I'm going to do here is, this here is obviously just a constant, so I'm going to bring that out the front. We also see here that if we push the m through, we have e to the negative m over n. That's just a constant, so we're going to bring that out the front as well. So that's why that component is there, and that's why that component is there. And what we're left with is the integral from 0 to infinity of u to the power of m, e to the negative u to the n du. And so all I've done in this next step is just using our indice laws, I've just combined it into one component of k. So this becomes k to the negative m plus 1 over n, and then we have the remaining component. Now, as I said, I want to put this in the form of the gamma function. The gamma function is of the form e to the negative to the power of just an x or a t or something like that. So if we just go to our definition of our gamma function, I'll use the one from Wikipedia here. We see here it's e to the negative x. So I want to replace it from the form that we have currently, which is e to the negative u to the power of n, to e to the negative t. And so I'm going to let t equal u to the power of n. And by doing that, that will replace this e to the negative u to the power of n, which just with just e to the negative t. And then this will be arranged into something that involves t to the power of something. And then as long as we do everything correctly, which we will, we can then put it into the form of the gamma function and we're done. Okay, so as I said, we're going to let t in this case equal u to the power of n, which means dt du is equal to nu to the n minus 1, which is equal to n. And remember here, u, so if we take this definition here, t is equal to u to the power of n. That means u is equal to t to the power of 1 over n. So when we've got u to the power of n minus 1, that's just t to the 1 minus n, n minus 1 divided by n, which is what we have here. So rearranging this, this becomes du is equal to 1 over n t to the power of n minus 1 over n dt, which is equal to 1 over n. All I've done is I'm just going to use the indices laws to bring this up, so you just raise it to a negative power, so we just swap these around. And we have t to the 1 over n dt, and then just separating this fraction out, this becomes 1 over n t to the 1 over n minus 1. So 1 over n minus n over n, which is where we get the minus 1 term, dt. Okay, now we now need to examine our bounds, just like we did in the previous substitution, and see how they change. So we now have, in this case, that u is equal to, we're going to t, my apologies, t is equal to u to the power of n. So when u is equal to 0 in our lower bound, we've just got 0 to the power of n. So the only value of n in which we would not be able to use in that case would be n is equal to 0. Because if n is equal to 0, that would be 0 to the power of 0, which is undefined. It has a limit, but it is undefined. We probably could actually get away with that, but I'm going to force it here that we can't have n is equal to 0. The other thing too, and this will come about in the next one, is that we also need n to be positive. So for our next component up here, as u, my apologies, goes to infinity, if we have infinity to the power of a positive value, that just goes to infinity. So we've got infinity to the raised to the positive, which is just an even bigger number, which would then obviously just be infinity. So that bound would remain unchanged. If, however, n was less than 0, then that would mean that infinity raised to some negative component would actually go to 0. So instead of it being u to the power of n, it would be essentially the same as 1 over u to the power of some value. And so in that situation, then, as it goes to infinity, 1 over infinity is equal to 0, which would change the bounds. We don't want to change the bounds. We want them to remain the same because, again, just going back, we want to have this definition here. Now, I'm forcing it to be put into the form of the gamma function. So in order for that to occur, this is what I'm imposing. Now, let me say, and I say this in my other videos, that does not mean absolutely that we can't deal with the situation of n being a negative value. It's just, if we want to express it in the form of the gamma function, which I'm doing here, we have to have it that n is greater than 0. So that actually might be something that I'll have to think about, whether or not how we would go about it. I have a feeling that it would be undefined because of the lower bound as well, because if we have 0 to the power of a negative value, that would be 1 over 0, which would go to infinity. Anyway, let's not worry about that at this stage. I will have to think about that. If people would actually like to see that exploration done, please comment or send me a direct message to let me know and I'll do up a video. Anyway, so we already had that k was greater than 0, and we now have a restriction that n is greater than 0. So n is a real value, but n must be a positive real value. Okay, so substituting everything in, we have j of k, n, which equals this quantity that we have here. So we have k to the negative n plus 1 over n. As I said, we've imposed this n is greater than 0, so our bounds remain unchanged, 0 to infinity. The term that we have here, u to the power of n, well, u is equal to t to the power of 1 over n, so we've got t to the power of 1 over n, raised to the power of m, e to the negative t, remember because t is equal to u to the power of n, so that's why we've got that here. And then our du component gets replaced with this expression that we have here, which is 1 over n, t to the power of 1 over n minus 1 dt, which is what we have here. Okay, so now let's just clean it up and we're done. So 1 on n is obviously just a constant, so we're going to bring it out the front, which is what we've done here. As before, the bounds remain unchanged. Here we've got a t term here, so we have t to the power of m over n, and we also have t to the power of 1 over n minus 1. So combining that all together, that's just m plus 1 over n, subtract 1. So just indice laws. E to the negative t dt. And so you'll see here, this is in the exact form of the gamma function. So let's have a look at it once again. The gamma function, gamma of z is equal to the integral from 0 to infinity of x to the z minus 1 e to the negative x dx. So it needs to be in this form of z minus 1. Now you'll see here the condition here is that the real part of z, so it does extend into complex values, must be positive. I'm only dealing with real numbers here, so that would be that the real part of z has to be positive. But in fact, actually, we can have the gamma function defined for negative quantities. It just is, there is a condition, and if you read through the full Wikipedia article, or the Wolfram Alpha article, you'll see this as well. It's defined for all values as long as z is not a negative integer. So just so you're aware of that. And so we're going to obviously have to impose that upon our integral solution here, because we're going to use the gamma function. Alright, so just going back to it, excuse me. So here we have here, so this is our z. This is our, see how we've got z minus 1? Our z value here is m plus 1 over n. So we just have that it's equal to 1 over n, so the stuff that we had at the front, 1 over n, k to the negative m plus 1 over n, times by gamma of m plus 1 over n. So that's great. We now have our solution to this, you know, I mean, I guess it is quite nasty. We've got 3 separate parameters here. As I said, this integral comes up a lot with a lot of the stuff that I work with, but we have now resolved it in terms of the gamma function. Now, for anyone who's watched my other videos, you'll often hear me go on about that I always try and make it as elementary as possible. To my knowledge, this is as basic, so to speak, as what the solution can get. I'm not sure whether or not this can be expressed outside of special circumstances without having to rely on the gamma function, which is a non-elementary function. That, however, is not so bad. I mean, I'm perfectly fine with the gamma function. It's just whenever we have the opportunity to replace it with an elementary function, we do that. So as I said, the condition is, though, that the z value here cannot be a negative integer, which is what we have here. So that is a further condition that we have to impose here. So we have, so therefore, putting it all together, my apologies, j of k, comma n, which is the integral from 0 to infinity of x to the power of n, e to the negative k, x to the n dx is equal to 1 over n, k to the negative m plus 1 over n, times by gamma of m plus 1 over n. And the conditions that we have is that n and k have to be positive, and that m plus 1 over n cannot be a negative integer. Now, if we have a look here, we haven't really talked so much about m here. So, well, yeah, as I said, the only condition is that involves m at this stage. M can just be any real value, but m must satisfy this relationship that m plus 1 over n cannot be a negative integer. So as long as we have these 3 conditions satisfied, this integral is convergent and it has a solution. Once again, though, to repeat, I am not saying that if these conditions were relaxed in some other context, that there could not be a solution representation in some other form. I took the route of using the gamma function, and by doing that, I had to impose these conditions. But if you explore it with other non-elementary functions, or maybe you can find an elementary way to go about it, you may be able to do it that allows us to be able to relax these in entirety. And if you can, please post up a link to your solution on this video, because I would absolutely love to see that. Okay, great. Well, that's all we have for this video. If you like the video, I just ask if you could please give it a like. If you would like to see more integrals of this nature, please subscribe. And, you know, as I say in all my videos, I take requests, so either comment here or send me a private message. And if I can solve the integral, I will certainly do up a solution and I will post it. Otherwise, I will see you in the next video. Okay, bye-bye.